My name is Nicholas Greene, and today I'll be presenting my work, Metrically-Scaled Monocular SLAM, using learned scale factors. This work was conducted with Nicholas Roy at the Computer Science and Artificial Intelligence Laboratory at the Massachusetts Institute of Technology. Our motivating problem is that of monocular SLAM, or simultaneous localization and mapping, where the pose of a single monocular camera is estimated as it moves through the environment. Many applications that could benefit from monocular SLAM, such as mobile robot navigation or augmented reality, require these SLAM solutions to be metrically scaled to be of any use. However, metric scale is difficult to recover. The traditional formulation of the monocular SLAM problem is ill-posed in that multiple solutions are valid at different scales without external information. In fact, when only the geometric content of the images is used for SLAM, the metric scale of the solution is fundamentally unobservable. One possible solution is to fuse the monocular camera with an additional sensor, such as an inertial measurement unit, or IMU. Although many impressive results have been achieved using this approach, visual inertial fusion has significant drawbacks. First, extracting metric scale from the IMU requires careful estimation of the accelerometer biases. Any errors in these bias estimates are doubly integrated into the position of the camera. If care is not taken, the IMU can cause the SLAM solution to quickly diverge by effectively running away from the camera. Furthermore, scale is only observable to the IMU under acceleration. Such otherwise unnecessary accelerations can be very dangerous for mobile robots, such as micro-air vehicles. Another possible solution is to train a neural network end-to-end to regress the pose of the camera from assembled images. This method has seen a surge of interest in recent years, given the rapid adoption of deep learning to various computer vision tasks. However, by training a network end-to-end, many of the observable constraints in the monocular SLAM problem, such as those generated by the epipolar geometry, are ignored. Is there a way for us then to use learning to infer just the metric scale, the single unobservable quantity in the monocular SLAM problem, while obeying the epipolar constraints generated by our sensor data? In this work, we develop a solution for this approach. We first leverage geometric monocular SLAM techniques to accurately estimate the relative geometry of the moving camera, and then train a coarse depth prediction network to provide the metric depths for the visible landmarks. The ratio of the unscaled depths from the SLAM graph and the metric depths of the network provides a measurement of the scale, which we can exploit to generate a fully metric solution. Our metric depth prediction network is based on the pyramidal structure developed by Pogue et al., but augmented with residual blocks to increase the expressiveness of the network and optimized for scale prediction. Features are first extracted from the input images at coarse image scales using 2D convolutions with residual connections. Disparities are then estimated at each image scale from these features using additional residual blocks. Disparities are passed between image scales using upsampling. Higher resolution disparity maps are also produced by simple upsampling. Since we are only interested in using the predicted depths for scale, spatially coarse depth predictions are sufficient, and expensive feature extraction and disparity estimation at fine image scales can be avoided. Using our architecture, predicting a 32 by 64 pixel depth map can be computed in as little as 30 milliseconds on a standard CPU. The losses we use to optimize our network are based on the self-supervised approach of Goddard et al., with additional supervision using traditional stereo block matching. Our training data consist of calibrated stereo image pairs. At training time, each image in the pair is passed through the network to generate a disparity map. These left and right disparity maps are then used to generate our training losses. At test time, however, only single monocular images are required to generate our metric depth predictions. The total loss of the network is composed of 4 weighted terms: a photometric loss that captures the consistency between the input images and those predicted by our estimated disparities, a smoothness loss that penalizes high-frequency noise in the disparities, a left-right loss that ensures the disparities from the left image and the right image are consistent with each other, and a supervised loss term that ensures that the coarse predicted disparities are consistent with high-resolution disparities computed by stereo block matching. Now, one could imagine integrating the estimated depths into the monocular SLAM graph in several ways. For instance, one could add the metric depths directly as factors on the landmark variables. However, visual geometry graphs of this type are typically implemented using over a sliding window of keyframes to bound computation time. This means that scale information can only be incorporated over a small fraction of the camera trajectory. Any noise in the metric depth estimates over such a short window could lead to errors or numerical instability. Instead, in addition to a local visual odometry module to estimate the relative geometry over a sliding window of keyframes, we introduce a separate global Sim3 pose graph to fuse the unscaled relative geometry with metric depths from our network in the form of unary scale factors. The global pose graph is constructed from keyframes marginalized out of the local VO graph and is able to fuse scale information over the entire trajectory, including loop closures, in order to more robustly lock on to the true metric scale. Each pose in the global pose graph is defined over Sim3, which is composed of a rotation, translation, and an explicit scale variable. This allows trivial integration of our metric depth data by adding unary scale factors onto the scale variable that measure the discrepancy between the current scale estimate and that given by the network. The accumulation of these scale factors over the entire pose graph allows the true metric scale to be accurately inferred. A flowchart of our entire pipeline is shown here. Monocular images are first processed by our local visual odometry module that generates accurate but unscaled keyframes. When these keyframes are marginalized out of the sliding window, they are then fed into a global pose graph that integrates metric depth measurements from our coarse metric depth prediction network. The fused metric keyframes can then be used to scale the output of the local VO module to achieve a live metric pose of the camera. By integrating the metric information encoded in the network in this way, we can achieve metric solutions without any additional sensors, compute, and without ignoring the constraints observable in the image data. We implemented our depth prediction network using TensorFlow and trained it using stereo images from the Kitty Vision benchmark suite. Our geometric SLAM pipeline was implemented in C++ using series. All SLAM and network inference was performed on an Intel i7 CPU. We show compelling odometry performance on the Kitty odometry benchmark, where we are significantly more accurate in terms of relative rotation error and relative translation error than end-to-end approaches, and competitive with hybrid approaches that require GPU acceleration. In the plots here, our approach, the blue trajectory, tracks the ground truth in red very closely as the nearest competitor, DVSO, in dash purple, which requires significantly more computation. Here we show examples of our pipeline running on the Kitty odometry benchmark. The ground truth pose is shown in red, and our global pose graph is shown in green. The coarse depth maps estimated by our depth prediction network are shown in the bottom right. As can be seen by how closely our trajectory in green tracks the red ground truth, our method is capable of estimating accurate metric poses using only monocular imagery. Finally, we also validate our approach on data collected from an indoor environment using a handheld stereo camera. We trained our depth prediction model on this data and then compared our SLAM solution when using only the left camera to that of the state-of-the-art stereo SLAM system, OrbSLAM2. The plots here show how our approach can consistently estimate metric solutions using only monocular imagery. In conclusion, we presented an efficient method for monocular SLAM that is capable of estimating metrically scaled solutions without any additional sensors, compute, and without ignoring constraints observable in the image data. We show competitive odometry performance on both the Kitty odometry benchmark and imagery collected from an indoor environment. We'd like to thank you for listening, and if you're interested in more details, we encourage you to read our paper and are happy to answer questions. Thanks.